Today I want to talk about finding the derivative of polynomials. You know, when you want to find the derivative of a function, it's pretty complicated. You got to go through that whole limit as h goes to 0 business. But I'm here to tell you, in the case of polynomials, there's actually a trick for doing the derivative, which makes it very, very easy. Very much easier, at least. From now on, actually, when it comes to polynomials, you will regard that thing with the limit as h goes to 0. That's the hard way. There's a much easier way for polynomials to find the derivative, and that's what I want to talk about today. The trick is pretty awesome, just because of how hard it is without the trick compared to how easy it is with the trick. As far as polynomials go, we have seen one example already. It was the derivative of x squared. We did this example a couple times ago. I don't know if you remember, but I'll just tell you in case you've forgotten. The derivative of x squared is 2x. Like I said, there's a trick actually by which you can figure this out instantly without going through that whole limit thing. And I want to talk about that trick in for other polynomials also. First off, a little notation. It's a little cumbersome to write this in sort of two steps like this. What I'm saying is the derivative of x squared is 2x. If you think of the derivative like an operation, there's actually a way to write this. So here's another way of writing. We write like this, d over dx of x squared equals 2x. So this right here is a special operation. We write it as if it were a fraction, but this doesn't actually mean any kind of fraction. This is just the way that we write the derivative. There are reasons to write it that way, which I don't want to get into. Sort of historical reasons. It's not really a fraction, even though we do write it with the bar. Anyway, this means derivative of, all right? And this x refers to the name of the variable in here. If my function was in terms of the variable t, I would write d over dt, or whatever other variable you like. All right, so this right here means the derivative of x squared is 2x. For our purposes today, it's usually going to be more convenient to write things using this d dx, although we will, when convenient, we'll still be going to be writing the primes. Yet another way to write this, which is related to this notation here, if your function is written as something like y equals x squared and you want to write the derivative of that, the notation for that is written like this. So if y is x squared, dy dx means the derivative of y, and in that example it would be 2x, because the derivative of x squared is 2x. Okay, let's talk about other polynomials. All right. We did x squared a couple times ago. Let's talk about like the next harder polynomial. How about the derivative of x cubed, right? What's the derivative of x cubed? Now, we don't know the trick yet, so I'm just going to do this by hand using the limit. This would be, I begin with the definition of the derivative. I hope you recall. Right, this is the limit h goes to 0, f of x plus h minus f of x divided by h. We begin by plugging into the function f of x plus h. This is my function f of x, and I'm going to plug in x plus h where I see x there. It will say x plus h cubed, and you best put them parentheses there, right? Minus f of x is x cubed divided by h, like so. And, you know, we keep going here. What do you got to do? You got to cube this. This is a real pain. This is like the FOIL thing, but you got to do it an extra time. I'll do it over here. X plus h, x plus h, x plus h. You into that? Probably not, but you got to do it. If I just multiply two of these, I'm being a FOIL master, I remember what happens when you just multiply the first two. You get x squared plus 2xh plus h squared, right? But then that I have to multiply by x plus h. And now you got to just distribute every possible pair. So I multiply the first one by each of these first. So this would be x. First I get x squared times x, which is x cubed. Next I get x squared times h, which is x squared h. You can't can't write that any differently. Okay, now I do the middle one times each of those. 2xh times x is 2x squared h, right? I have two x's and just one h. Then I have 2xh times h. That would be 2xh squared, because that has two h's in it. And then finally, the h squared gets multiplied by everything. I get h squared x plus h cubed, right? H squared times h is h cubed. Okay, some of these can combine. I have x squared h plus 2x squared h. That makes 3x squared h. Then I have 2xh squared and another h squared x. Those are the same, so I can combine those and make 3xh squared and then h cubed. All right, that's the result of multiplying out this thing 3 times. So up here, that goes in that position right there. Lim h goes to 0. So right here, I'm going to write all of this. X cubed plus 3x squared h plus 3xh squared plus h cubed, right? That's right there. That was only this part. So next I go minus x cubed. Divide everything by h. Okay. And we can, hopefully, can anything cancel here? I think the x cubed. I have x cubed there, minus x cubed there. So those cancel. And everything else here has h as a factor. So I'm going to factor the h out on top. This is like we always do. Factor the h out on top. What remains? 3x squared plus 3xh plus h squared, right? Divide by h. We cancel the h's. At this point, we can actually do the limit by plugging in h equals 0. So I just get 3x squared plus 3x times 0 plus 0 squared. And those are both 0. So the whole answer is just 3x squared. Okay. So far, we have said derivative of x squared is 2x. And then what we just did said derivative of x cubed is 3x squared. All right? I want to try and look at these and see if there is some kind of pattern. In fact, there is a pattern. You could do, if you wanted to, this would be a pain to work this out, you could do derivative of x to the 4 just in the same way that we did x to the 3. The hard step would involve multiplying out x plus h, the whole thing, to the 4th power. You'd have to do like the FOIL thing, but 4 times. I had to do it 3 times here, which was hard enough. This would be even harder. Would you mind if I just told you the answer? If you worked out all those details, you would find the answer to be 4x to the 3rd. All right? Can we look at these? Do you see any pattern here? If you look at this thing, and then how does this thing relate to the answer over here? I think you will see a pattern. The pattern is the exponent here turns into a coefficient in the answer. It happened there. It happened there. It also happened here, right? The 2 came down and became a 2 coefficient. And the new exponent in your answer is simply reduced by 1 from what it used to be. So this 3 became a 2. This 4 exponent became a 3. And even here it works. Remember, 2x is the same. This really means 2x to the 1, right? And so you can see again, the 2 up here, the exponent, becomes a coefficient. And then the new exponent is just 1 less than what it used to be. So the rule in general, can I write the rule in general? If you have a polynomial that just is one thing, a monomial, remember that word? Not a word you use all the time. If you have something like that, the answer is always this exponent becomes a coefficient. So I'll write n. And then we have x to some power. The new exponent is just 1 less than it used to be before. That would look like that. All right? Put this in a box. You can tattoo this on your arm. This we're going to use all the time. This is really one of the sort of foundations of most of what we do, like throughout the whole semester. You're going to do this every day, probably, almost every day. Very important. Also very easy, right? There's no, you just have to remember how to do this. But I would say memorize it, but you're definitely going to remember that because we're going to do it all the live long day, all right? We should discuss, this is x to the power n, and it works for any n. So this works for any n. It really does. I mean positive or negative numbers. and also even non-whole numbers, like exponents which are not whole numbers. I just said it twice. Exponents like fractions. This works also for exponents like fractions, although the argument to see why is much more complicated in that case. But would you take my word for it? This works for any n. Can we talk about, just as a special case, what if it were just x, no power, just the derivative of x? Well, that's easy enough. You can go through the thing with the limit on this. It's not hard to do. Or you can just realize that I'm asking you, what is the derivative of x? On a graph, the function y equals x, it looks like this, right? And don't you know, the slope, this is a line, and its slope is always 1, isn't it? And so the derivative here is just the constant 1. So you could think this is like a special one that you just have to remember separately from this formula. Although it does work if you use this formula here. If you think of this as x to the power 1, the answer will be 1 times x to the power 0. X to the power 0 is also 1, so you get 1 times 1, which is 1. Anyway, this is, you could think of it as a special case of this formula. This is what you do if you see x with no exponent. You just get 1. And also, one last special case. What if you are looking at the derivative of something which is just a constant? Say a number, a specific number. So this c is a constant. All right? It could be 0, could be anything. What's the derivative of just a constant? Again, we can just think of it in terms of the graph. A constant function, if you recall, looks like a horizontal line, right? And what is the slope of this line? Along this entire line, the slope is always 0. 0 slope means horizontal, which it is horizontal. So the derivative of any constant is 0, all right? Put these three together in your mind. You can find the derivative of any x to any power, including x to the 1 power, or just a constant. A constant, the derivative of a constant is always 0. Excellent. A few very simple examples. Now that you know that trick, all these examples will be very, very easy. So how about, what is the derivative of x to the power 10? What do you say? Don't think too hard about this. Just do the trick. The trick says the exponent becomes a coefficient in the answer. So I put 10 as a coefficient. And then the exponent, so I have x again, and then a new exponent. The new exponent is always 1 less than the original exponent. So it's 10x to the 9. That's all there is to it. How about some more? How about this? X to the minus 3 power. Remember, that means the same as 1 over x to the 3rd power, although you don't have to think about that. Remember I said you do the same trick. This trick is called the power rule. You do the same power rule even for a negative exponent. It still works. So we take the exponent, becomes a coefficient, and then I have x. And what is the new exponent? You decrease the original exponent by 1. Be a little careful here. What is minus 3? Decrease it by 1. It becomes minus 4. Did you think it was going to be minus 2? It's not. You decrease by 1. If it was negative, it becomes even more negative. All right? So that's the derivative of x to the minus 3. How about x to the minus 1, also known as 1 over x, right? This, of course, is the same as the derivative of 1 over x, because 1 over x is the same as x to the minus 1. Anyway, what's the actual answer? The derivative of this. Look at this one. This one is more convenient than this one because it has a power. So here, I move the power into the front, as we always do, and then I decrease the power by 1, and it looks like that. So if you like, you could write it as minus x to the minus 2. I don't care how you write it. Either way, fine with me. All right? That's the derivative of x to the minus 1. Would you mind me saying, there's something truly sort of almost transcendently awesome about this trick. It takes a concept which on its surface is very complicated. The derivative takes some function and gives you another function which describes the slope of the tangent line of the original function. To me, that sounds really complicated. To me, there's no reason to expect that such a thing could have such an easy trick to find the answer. But it turns out there is a very easy trick to find the answer. This seems strange to me that such a complicated concept can be computed by such easy methods, right? All you got to do is do this little trick with the exponents and the constants. This kind of thing is the kind of thing that mathematicians identify as mathematical beauty. There's many types of mathematical beauty, but one of them is when something really ought to be very complicated but turns out to be very simple, just for magical reasons. And what are we to think about those magical reasons? It's not like a piece of technology which seems to work by magic. It's not magic. It's because somebody made it to work in that way. This is how technology works. But mathematics, why is mathematics work that way sometimes, where something ought to be more complicated than it truly is? Because nobody made this, it just is, right? This is a beautiful and transcendent, deep fact about the nature of the universe and our position in the universe, I think. Hey, this is what mathematicians are into. This is what I'm into. You may have noticed by now, I'm not really into numbers per se. Numbers to me are useful, but facts that things like this are what really interests me about mathematics. I don't know if you think that's interesting or not, but that's just me. Some more rules about derivatives. There are two very important rules about the derivative, which has to do with what happens if you take the derivative of a sum of things, or what happens if you take the derivative of a constant multiple of a thing. I'm referring to something like this. If you have two functions and you're adding them together, and you want to know what is the derivative of the two things added together. If you think of this in terms of rate of change, actually I think it becomes pretty clear what the answer should be. I'm asking you, I have two different things and I'm adding them together, and I want to know how fast is the total sum changing. Well, that's the same as how fast the first one is changing, and you add that to how fast the second one is changing. It's like if I have two investments, I'm invested in Apple and Google, right? And my Apple investment, I'm talking about like stock market. My Apple stock is changing in a certain way. My Google stock is changing in a certain way. What if I ask you, how much is, like, if I add those two stocks together, how much money I have invested? Just like my total investment. How fast is my total investment changing? Well, that would be the same as taking how fast the Apple is changing and adding it with how fast the Google is changing. Anyway, what I'm saying is the derivative of two things added together is the same as adding together the two derivatives. This is derivative of f of x plus derivative of g of x, right? How fast the sum is changing, it's same as just adding together the changes in the two sums. This is what I said about sums. It's also true for constant multiples. This one is maybe a little harder to see why, but it is true. Derivative of a constant times f of x is the same as a constant times the derivative of f of x. So this is like if I have something which is changing and I just multiply all the values by 2. If you think about it on a graph, multiplying everything, say, by 2 stretches vertically the entire graph by a factor of 2. This will stretch all the slopes to be twice as steep as they used to be. And so if you think of this in terms of the graph, this is like the slopes of after I multiply the graph by 2, those slopes will be the same as 2 times the original slopes. That's what this is saying. All right. Anyway, these two things are super important. I would say you need to memorize these, but again, you're going to be doing these so often that you will just unconsciously do this at all times. So you don't really have to memorize them. Now that we know those rules about constants and adding, we can do many more examples than we could have it's not any harder really. How about derivative of 3x to the 7? What's that gonna be? All right, first of all, you use the rule about the constants that I just wrote. If I have a constant inside a derivative, you can pull it out of the derivative. So this is 3 times derivative of x to the 7. Come on now. X to the 7. And now this, using the power rule, I make the 7 into a coefficient. So this is 3 times, and now I'm going to do this by itself. 7 as a coefficient, x to the power 6. All right? And now I'm done. I did the derivative. You can just multiply 3 times 7 is 21. X to the power 6. All right? And there you go. Now, this, I wrote it out in several steps. But actually, once you get used to this, you can just jump immediately from here to here. How do you do that? I'm just going to say the 7 comes down and multiplies onto the 3, and I get 21. And then the 7 decreases and becomes 6. That's all there is to it. How about derivative of, I don't know. I mean, these really don't get any harder than that. 8x squared. The 2 comes down to the front and multiplies onto the 8. I get 16 x to the power 1 because the 2 decreases. That's all there is to it. How about, check this one out, derivative of 5 over x to the 4. This one's a little tricky. This division is not something that we've discussed yet. So we know how to do individual powers of x, or constant multiples of such, or additions of such. But this division actually requires a special rule, unless you know just a little trick. The little trick is, don't write it as an addition, write it as a negative exponent. So this is the same, I'm writing d dx here because I didn't do the derivative yet. This is the same as 5x to the negative 4, right? This is what I mean by write it as a negative exponent. This is much more convenient because we already know how to handle exponents. The minus 4 comes down here, multiplies onto the 5. I get negative 20 x to the minus 5. I decrease the power by 1. And that's the answer. How about that? So you can now do any power of x with any coefficient in front of it. All right, this is the constants rule. And the addition makes this even better. If you pair that with the addition rule, you can do any polynomial now. How about this? How about derivative of, let's just say, 6x cubed minus 8x to the 7 plus 3 minus 5x. Can we do this polynomial, the derivative of everything? Now, when you have a derivative of a bunch of things added together, you just do the derivative of each individual thing. That was the rule about sums, derivative of a sum of things. Here I have a minus rather than a plus. It doesn't matter. You can do the same thing with a minus, because a minus is the same as plus with a negative coefficient, and everything works out nicely with the coefficients. So what we got to do is just go down the line here and take the derivative of each part. What do you get? From this part, I do the power rule. The 3 comes down, multiplies onto the 6. I get 18 x to the 2, because I decrease the power by 1. All right, minus, what happens here? Same business. The 7 comes down, multiplies onto the 8. 7 times 8 is 56. X to the power 6, right? Decrease the exponent by 1. Plus 3. What happens to 3? This is one of those special cases I said before. Do you remember, what do you do when you have the derivative of a constant? It is 0. That you just have to remember. The derivative of a constant by itself with no x is also always 0. And then what about this? Minus 5x. The minus 5 is a coefficient. Will stay like it is. How about the derivative of x? This also, I hope you remember, was a special case. The derivative of just x is 1. And so when I do this last part, it becomes minus 5 times 1, which of course is just minus 5. So my whole answer, if you want to just omit the extra parts, my whole answer is that. 18x squared minus 56x minus 5. Derivatives of polynomials. You can do any polynomial in this way, right? There's nothing special about this particular example. Change the numbers around however you like. You can still do it very easily, like so. I got 2 more examples involving rewriting. The basic slogan is rewrite things as powers, because the power rule involves powers of x. If you have a formula which doesn't necessarily look like powers of x, then you got problems, and it's best if you can rewrite everything so that it does look like powers of x. So 2 examples in that vein. How about the derivative of x to the 5 plus 3 square root of x plus 7 over 2x. How about that? Can we do this derivative? Now, I'm a little worried when I see something that's not written like a power of x. That would be here and also here, right? These concern me. This one because I have a square root sign, which is not a power, and this one because I have x is inside a denominator, so x is not being written as just an x to some power. So I'm going to try and rewrite those parts. This step, I am not yet doing the derivative. I am just rewriting the inside. Now, x to the 5, I'm not going to rewrite because I already like the way that looks. So x to the 5 stays like it is. 3 root x. Can we rewrite that part as a power of x? Actually, this is something I hope that you remember. The square root of x can be written as a power. It is x to the 1/2 power. Now, usually, this is not a more useful way of writing than the square root. But in this class, actually, it is almost always better to write things. If you see a square root, you basically should always immediately change it into a 1/2 power, because the derivatives are so easy to do with power. So when you see roots, always rewrite them as powers. The square root is the 1/2 power, the cube root is the 1/3 power, and so on. Okay, and what about this one? Can we rewrite this as a power of x? Well, when you see x inside the denominator, you should try to write this as a negative exponent. This one, I can move the x up and turn it into an x to the minus 1. So I'm going to write it as 7 over 2 x to the minus 1. Don't also bring the 2 up. The 2 really belongs in the denominator. If you want to bring it up, you also would have to write 2 to the minus 1, which is 1/2. And you might as well just keep it in the denominator in the first place. Okay, so when you see x in a denominator, you can move that up and write it as a negative exponent. In this case, just x becomes x to the minus 1. If it was like x squared, it'd be x to the minus 2. And so on. Okay, now everything is written as powers, and now I can take the derivative of everything by using the power rule. So x to the 5 becomes 5x to the 4, plus 3x to the 1/2 becomes, all right, the 1/2 comes down and multiplies by the 3. So it's 3 times 1/2 x to a new power. The new power is going to be the old power minus 1. What is 1/2 minus 1? It is negative 1/2, right? 1/2 is like 0.5, and if I subtract 1, it becomes negative 0.5. Okay, finally, 7 over 2. That's just the coefficient, which stays like it is. The minus 1 comes down in front, and then I get x to the minus 2. All right, this is my answer. I took the derivative. You can leave your answer like that, although if you insist on sort of doing little simplifications, it'd be 5x to the 4 plus 3/2 x to the minus 1/2 plus, this I guess would be minus, because I have a minus there, minus 7/2 x to the minus 2. All right. Now, probably you were coached as a high school student to always simplify everything. I don't really care about that. I'm going to assume that you know how to simplify things, but this right here, to me, is an acceptable answer. Your job was to find the derivative. That is the derivative. Whether you want to write 3 times 1/2 or 3 over 2, I don't care about that. This is the derivative. You can simplify it if you want to, but unless there's a good reason to, I'm typically not going to try to simplify the answers. One more example. All right, this is also along the general theme of you gotta rewrite things in terms of powers of x. What's wrong with this is that I have this big fraction. Now, here's a little beware. Do not simply take the derivatives of all of these across the top and then also take the derivative across the bottom. That's wrong. You actually are not allowed to do that. When you have a big quotient like this, a big fraction, there is a special rule for dealing with that as a fraction. It's called the quotient rule, but we're not going to talk about that just yet. Actually, this one you can handle by rewriting everything in terms of powers of x. And the strategy here, again, if you have a power of x in the bottom, move that up and write it as a negative exponent. So I'm going to write this as, I'm not doing the derivative yet, that's why I still wrote this. I'm just redoing the inside. X to the 6 plus 3x minus 5. Instead of divided by x cubed, I'm going to write it as times x to the minus 3. All right? Make sure you put those parentheses there. That's important. Why did I do that? It's because now this can be distributed across the first part. So this is derivative of, and when you distribute, I hope you remember what happens when you multiply x to the 6 times x to the minus 3. You add the exponents. So what I get here is x to the power, and in the exponent I'm going to see 6 plus negative 3, which is 3. So you add the exponents, I get x to the minus 3, plus the next one has a 3, and then x, and x to the minus 3. I add the exponents, I get x to the minus 2. And then finally minus 5 x to the minus 3. That one's easy. You don't have to deal with adding exponents or whatever. All right. Hey, check it out. I did that, and now it just looks like an ordinary polynomial, and I can just take the derivative term by term the way that I like to do. So the derivative of x cubed is 3x squared. Come on, man. Plus the derivative 3x to the minus 2. The minus 2 comes down, multiplies by the 3. I get minus 6. So actually this plus is really a minus 6. And then x, I decrease by 1. It was negative 2. I subtract 1. I get negative 3, right? And then this one, the minus 3 comes down, multiplies the minus 5. I get plus 15. X, I decrease negative 3. by 1, it becomes negative 4. That's that.